In this lecture, we're going to discuss redox reactions or oxidation-reduction reactions. So first, we'll do a brief review of redox reactions. We'll define oxidation and reduction and remind ourselves how to balance an oxidation-reduction reaction. And then finally, we're going to introduce electrochemical cells. It's very important to understand that an oxidation-reduction reaction is a reaction that involves electron transfer. So oxidation and reduction take place simultaneously. Redox is a two-way process. So if some compound is reduced, then some other compound must be oxidized. Those two things are happening simultaneously. In oxidation, a species loses electrons. So for example, lithium is a group 1 metal. It's energetically favorable for lithium to lose an electron to go to lithium plus, so that lithium is isoelectronic with helium. In reduction, a species gains electrons. So for example, all of the halogens often readily undergo reduction, such as diatomic chlorine picking up 2 electrons to go to 2 chloride anions. You might be familiar with the mnemonic device, Leo the lion says grr. This is a mnemonic device to help you remember the difference between oxidation and reduction. So Leo, lose electron, is oxidation, and grr, gaining electrons, is reduction. There's also another mnemonic device that you'll sometimes see, oil rig. So for oil rig, oxidation is loss, reduction is gain. So here we're talking about what is oxidation and what is reduction. We also need to think about oxidizing agents or oxidants and reducing agents or reductants. So oxidizing agents cause oxidation in other reacting species. So if you're causing something to be oxidized, you're taking electrons from something so that it will lose electrons. So making other reacting species lose electrons is the characteristic of an oxidizing agent. So oxygen is a good oxidizing agent. So are the halogens. And like we had already mentioned with chlorine, chlorine readily picks up 2 electrons to go to 2 chloride anions that are both isoelectronic with argon. So chlorine is an oxidizing agent. It's picking up electrons, so it's causing some other species to lose electrons. Whereas a reducing agent causes reduction in another species. It makes other reacting species gain electrons. So the group 1 metal that we were just discussing, lithium, we know loses an electron pretty easily to go to that noble gas configuration of helium. And in the process, it's causing some other species to pick up that electron. So if lithium and chlorine were to react together and form lithium chloride, lithium solid would be the reducing agent and it would be oxidized. And chlorine would be the oxidizing agent and it is reduced. We need to talk about the steps for balancing a redox reaction. So the very first step, sort of step 0, I'm going to just put it up here. The first step is we have to determine, is this a redox reaction? And the way that we can determine that is by assigning an oxidation number to all of the atoms in the balanced reaction. And if we have a change in oxidation state, then it is, in fact, a redox reaction. So first step is to assign oxidation numbers to all of the atoms. So let's just remind ourselves about oxidation numbers. So elements that are in their elemental state have an oxidation number of 0. So diatomic hydrogen, chlorine. Another example would be diatomic nitrogen. Anything in its elemental form will have an oxidation number of 0. And if you have a monoatomic ion, such as chloride anions or lithium plus cation, the oxidation number is equal to the charge of the ion. So lithium plus has an oxidation number of +1. Okay, now if we're dealing with compounds such as carbonate or calcium carbonate, or if we're dealing with chromate or something like that, we need to start thinking about what are the typical oxidation numbers for certain elements. One thing that we know is that oxygen typically has an oxidation number of -2. There are some exceptions, such as peroxide. Oxygen will have an oxidation number of -1, but typically oxygen will be -2. And hydrogen is typically +1, such as in water, but there are some examples where hydrogen is something different, like lithium hydride. In that case, oxygen has an oxidation number of -1. And then fluoride will always have a -1 oxidation state. And most of the other halogens will also be -1, but there are some exceptions. So sort of the takeaway here is that oxygen is typically -2, hydrogen is typically +1, and your halogens are typically -1. Also important to note that the sum of the oxidation numbers will equal the overall charge of the molecule or ion. Let's assign the oxidation numbers for this redox reaction. Zinc is in its elemental form, so it's going to be 0. Copper 2+ is the monoatomic ion, so it's going to be +2. Zinc is +2. Again, it's a monoatomic ion. Copper is 0. So this is very simple oxidation numbers for this first example. And because we have a change in oxidation number, we know that this is, in fact, a redox reaction. Zinc is losing electrons. Copper is gaining electrons. So it's an oxidation-reduction reaction. So the next thing we want to do is determine which elements are undergoing oxidation and reduction. We already said Leo the lion says grr. So the species that is losing electrons is being oxidized, and the species that is gaining electrons is being reduced. So zinc is going from a 0 oxidation state to a +2 oxidation state. So that means that each atom of zinc is losing 2 electrons. So zinc is oxidized, therefore it's the reducing agent. And copper is going from a +2 oxidation state to a 0 oxidation state. So it's being reduced and is therefore the oxidizing agent. So then we want to write out the half reactions for these substances. So for number 3, we can say that zinc is losing 2 electrons, so it's going to zinc 2+ plus 2 electrons, and copper is picking up 2 electrons. So for oxidation, we're showing the electrons as a product, and for reduction, the electrons are a reactant. And then we add those half reactions together. So what's really critical here is because this redox reaction is electron transfer, these electrons must cancel out on either side of the reaction. And in this case, they do. If not, we'd have to multiply this reaction by a coefficient to get everything to cancel out appropriately. So our overall reaction is zinc metal plus copper 2+, forming zinc 2+ plus copper solid. An electrochemical cell is a device in which an electrical current, or the flow of electrons through a circuit, is either produced by a spontaneous chemical reaction, or sometimes we will drive a non-spontaneous chemical reaction using an electrical current and an electrochemical cell. So galvanic cells, or sometimes also called voltaic cells, are spontaneous And electrolytic cells are non-spontaneous. It's when you use electricity to drive a non-spontaneous reaction. But both of these two are both types of electrochemical cells. Okay, so we need to talk about the different parts of the electrochemical cell. First of all, we have the anode. The anode is where oxidation takes place. In an electrochemical cell, the anode is where the electrons are lost. So electrons are moving from the anode to the cathode. And then to maintain charge neutrality, ions will flow through what we call a salt bridge. So the salt bridge is just some sort of porous separation. It could be something as simple as a plastic grid that's simply separating the two electrodes, or it could be some type of porous material that allows ions to move through. The cathode is where reduction takes place. So like I said, electrons are moving from the anode to the cathode. We can remember this from the mnemonic red cat. So reduction takes place at the cathode, or an oxidation takes place at the anode. So when we're writing a galvanic cell or any type of electrochemical cell, we always write the anode on the left and the cathode on the right in alphabetical order. We also need to mention cell notation. So cell notation is what is this right here. So this double line indicates where the salt bridge is, so the separation between the anode and the cathode. And then, so everything on the left are all the materials that are present in the anode. Everything on the right is everything present for the cathode. And sometimes we omit spectator ions. So these are the primary species that are present, that are participating in the redox reaction. And the single line denotes just simply a phase change. So we have solid zinc and aqueous zinc 2+. This is a figure from the Silverberg textbook that's just showing the exact same electrochemical cell. We've got zinc anode, copper cathode, and we have our zinc half reaction, our copper half reaction, that overall give us this balanced reaction. So as this reaction takes place, you'll notice that we lose zinc from the zinc electrode and we gain copper on the copper electrode. The flow of electrons arises from the potential difference. So E naught of the cell is the cell potential when the products and the reactants are in their standard states. Remember, we talked a lot about standard state conditions back in Gen Chem 2. So we're talking about 1 molar concentration, 25 degrees Celsius or 298 Kelvin, 1 atmosphere. These are the standard state conditions. The way that we calculate E of the cell, E naught of the cell, we take the reduction potential of the cathode and subtract off the reduction potential for the anode. And the overall free energy change, so Gibbs free energy, is related to that cell potential. So delta G naught is equal to negative N times Faraday's constant times E naught, where N is the number of moles of electrons that are being transferred. F is Faraday's constant, which is 96 kilojoules per volt. And E naught is the E naught of the cell, which is the reduction potential of the cathode minus the reduction potential of the anode. So you'll notice that if E naught is positive, then delta G naught will be negative. So if the cell potential is positive, the reaction will be spontaneous. If E naught is less than 0, it's non-spontaneous. If E naught is equal to 0, we're at equilibrium. It's not spontaneous in either direction. And if E naught is greater than 0, then it's going to be spontaneous in the direction that it's written. I just mentioned that we calculate E naught of the cell by taking the difference of the reduction potential of the cathode minus the reduction potential of the anode. So the way that we look up reduction potentials is in a table. Your textbook has a table like this that has a list of all of the reduction potentials. So you'll notice that Lithium has a very negative reduction potential, and that's because this reaction is spontaneous in the reverse direction. This is not favorable for lithium to pick up an electron and go to lithium metal. Whereas fluorine, the reduction potential is very positive and large. So that means that fluorine to pick up 2 electrons and go to 2 fluoride anions is favorable and is going to be spontaneous. You don't need to memorize the cell potentials. You simply just want to look them up. But something to keep in mind is that the more positive the reduction potential, the better oxidizing agent. The more negative the reduction potential, better reducing agent. All right, if we go back to our example and we wanted to calculate the cell potential for the reaction of zinc being oxidized and copper being reduced, we have our 2 half reactions. Now these are both the reductions, but remember that the copper is actually being reduced and the zinc is being oxidized. So that's why we take the cathode reduction potential and subtract off the anode reduction potential. So we do E naught of the cell is equal to E naught of the cathode minus E naught of the anode. So this would be 0.34 minus negative 0.77, which would be 1.103. So this reaction will be spontaneous because E naught for the cell is positive, so therefore delta G will be negative. I wanted to also mention that, so the example we just talked about, the copper and the zinc were both active electrodes, but you can also have inactive electrodes, such as graphite and platinum, where they're not part of the actual overall reaction. So here we have iodide that's being oxidized to form iodine, and MnO4 that's being reduced to form manganese 2+. So in this case, there's no solid metal that can act as the electrode. So, all right, let's do a quick example. This one's a little bit different. Copper is on the anode side, the oxidation, and tin is now on the cathode side. So the first thing we want to do is just to draw the cell and calculate the standard potential. So if we were to draw this, all right, so this is our anode. On the anode side, we have copper metal, that's the electrode. On the cathode, we have tin metal as the electrode. So let's just write out what this reaction is. So this would be our oxidation half reaction and our reduction half reaction. So we know that the copper is at the anode, reduction is at the cathode. So if we want to do E naught of the cell, we're going to take the reduction potential for the cathode, which is tin, negative 0.14 volts, and we're going to subtract off the reduction potential for the anode, which is 0.34 volts, and we get E naught of the cell is equal to negative 0.48 volts. And then we could go one step further and calculate delta G naught. And we would get that delta G naught is 92 kilojoules positive for every mole of copper that's oxidized. So this is non-spontaneous. And therefore this is going to be an electrolytic cell.